Remember the days when software wasn't all about flashy GUIs? When the command line reigned supreme and applications were as fast as they were functional? Terminal user interfaces, or TUIs for short, aren't just relics of the past. They are fast, lightweight, and perfect for certain tasks even today. And if you're a developer working in Rust, you're in for a treat. In this video, we're diving into Ratatui, a fantastic Rust library for building TUIs. Ratatui gives you everything you need to create responsive, interactive, and visually appealing terminal applications with ease. From layout management and widgets to powerful customization options, Ratatui turns your terminal into a canvas for creativity. This video is more than just an overview, it's a hands-on tutorial where we'll build a simple but functional TUI step by step. By the end of this video, you'll have the skills to start creating your own TUIs using Ratatui and unleash their full potential in your projects. My name is Max, this is Green Tea Coding, and you should be sure to fire up your favorite code editor right now, because we get started in a second. Our goal today is to build a TUI from scratch that tracks and displays the progress of a task running in the background. Along the way, we'll explore how to keep the TUI responsive even when performing blocking computational operations. To achieve this, we'll implement a multi-threaded setup where threads communicate seamlessly with each other. By the end, you'll have a flexible and reusable framework that you can adapt for your own applications. But don't worry, we'll start with the basics. Let us of course start off by adding our dependencies. We will need Ratatui, of course, but we'll also need crossterm. Well, why do we need crossterm? Crossterm is a terminal backend that is required when you want to use Ratatui in order to generate TUIs. Let's have a quick rundown of why this is required. At its core, Ratatui serves as a high-level abstraction for creating terminal user interfaces. But how does it actually interact with the terminal? The answer lies in terminal backends. Terminal backends are designed for low-level terminal manipulation. They provide essential features like handling input events, controlling the terminal screen, managing text styling, and interacting with raw terminal modes. Ratatui builds on this foundation, using terminal backends to handle the intricate details for terminal communication, so you can focus on designing and building your TUI. One of the most popular backends is crossterm, and it's also the default when using Ratatui. With crossterm as the bridge between Ratatui and the terminal, you get portability as crossterm supports multiple platforms seamlessly. This means your Ratatui-based TUI can run on Windows, macOS, and Linux without modification. Let us now start coding. In order to have a central place where all our logic is stored, I'll create a struct called app. And this app for now will only have one Boolean member, which is an exit flag, i.e. when this flag should go to high, then our application should stop. We'll then have to set up our main function. At first, I want to make sure that any errors that will come up, and those will all come from an IO type, can be just bubbled up, so I'll use this std.io result and return it from a main function. Then the first very important step we always have to do in every Ratatui app is we have to initialize Ratatui. And what we get back is a terminal. This is very important because the Ratatui init step sets the terminal into raw mode. And because this is so important, let's just quickly talk about what raw mode is. Raw mode is a configuration for terminal input where the usual line buffered behavior is disabled. In this mode, input is passed directly to the application as it is typed, without being processed by the terminal, whereas in normal mode the terminal reads inputs only after you hit enter. Features like line editing, input echoing, and special key combinations, for example Ctrl+C for interrupting, are turned off, giving the application full control over the input. This is particularly useful for interactive applications like TUIs, where fine-grained control over user input is required. However, since raw mode bypasses many conveniences provided by the terminal, applications need to handle input and behavior carefully to ensure a smooth user experience. So now that our terminal is in raw mode, let's create an instance of our app, and it's gotta be mutable because of course we want to set this exit boolean in case we want to exit. And now we want to run this application in an endless loop. For this we will create later on a method called run, which takes in a mutable reference to the terminal. And in turn, anything goes wrong, we want to return this as a result from the app. After this, we want to restore Ratatui. This has to be done because the terminal was set into raw mode and we want to set it back into normal mode, and this is what the Ratatui restore does. And of course, in the end, we'll return our app result, which will be an IO result. So now that we've set up the main function, of course, it's time to implement our app. The first thing that comes to mind is we need to have this run function that we defined up there. And this one will take a mutable version of self, so we would like to change our state while the app is running. And then we'll take in a terminal, which is a mutable reference to a default terminal type defined by Ratatui. And of course, we're gonna return an IO result because things could go south in here and we just wanna bubble up any errors. So as it turns out, terminal user interfaces have a lot in common with graphical user interfaces. The core of everything is an endless loop that just re-renders as long as we're not exiting. So in the loop, we'll access our terminal and call the draw method. The draw method expects to receive a function that takes a frame as an argument and then does some kind of drawing with the frame. In this case, we will use a lambda that just forwards the call to the draw method we'll be implementing on our abstract. And of course, we want to bubble up any errors here. Finally, after our main loop is exited, we'll return an OK to satisfy the IO result return type. Now, of course, we don't have the draw function yet, so why don't we just go and implement one? While drawing, we don't want to mutate the app state, so we'll just have a immutable reference to self. And of course, we'll take in our frame, which is of the type frame from Ratatui. The most important function that frame has is it can render a widget, which is another analogy to GUIs, right? Where widgets are commonplace. Render widget expects a widget to be drawn, as well as an area in which to draw the widget. For the area, we can go with the whole frame area, as our TUI should use the whole terminal. However, we don't have any widget we could draw, yet. A widget is any struct that implements Ratatui's widget trait, so you could define a separate struct here. It is common for smaller applications though to implement the widget trait for the abstract directly, to have all the rendering logic in one place. So we'll hand self over to the render widget method. Let us now implement the trait widget for our app. We implement the widget trait on a reference to the app type because our render function does not modify any state. Using a reference ensures that the app instance remains available and unchanged for use after the draw function completes. The widget trait defines only one method, which is called render. And in here, we'll have a Ratatui rectangle, which again is the area in which we want to render, and a Ratatui buffer, which is the buffer we want to render to. For now, let's keep it very simple. We just want to render a title in the top of the layout. So what we do is we create a line, which is a kind of widget that Ratatui has built in already. And we can create this line from a string literal, and we'll just say process overview. And now we can style this a bit. Let's say I want this to be bold. And then we'll render it. And again, we'll need an area and a buffer. Well, What luck that we have area and buffer right here. By the way, if you're still contemplating this reference to app on the impl widget for app, I can show you exactly why we did this. For example, if we wanted to, let's say, change the exit state in here, so let's say self.exit is equal to true, we immediately get a compiler warning that we cannot assign self.exit, which is behind a reference. And it's behind the immutable reference to the self. So we use this concept of implementing the widget on a reference for the app rather than on the app itself, so that we cannot by mistake mutate some state here. So now the big moment has finally come. We can run our first Ratatui app. As you can see, I'm in the Windows PowerShell here, but as I said, cross-term enables you to work with a lot of shells, so it should be working for you wherever you are. We'll run this one, compile it for a second. And finally, there we have it, our process overview in the title. So let's just quit this with Control-C, because that's how you exit out of any terminal application, right? Well, it doesn't seem to be working. Why? Because we're still in raw mode. And as I said initially, raw mode does not have any of the conveniences that you have built into a normal terminal mode, but you have to handle all the inputs yourself. So the only thing left to do here is we'll have to close the whole terminal, because otherwise we cannot end our application. So it's quite clear what we need to do now. In our main loop, we need to watch for new events, especially key events from the user. So what we can do here is we can use cross-terms event read function. And this function blocks until new input is received. And once new input is received, we can match on this new input. And in this case, the only thing we're really interested in would be a key event. And we'll destructure it into this variable. And then we'll write a function which we don't have yet, which will be handle key event, and we'll give the key event to it. All the other things, we don't really care right now. There is a lot of other events that can come, from mouse inputs to size changes or whatever of the terminal. Right now, we're not really interested in that. Of course, we need to implement our handle key event function. We want to have a mutable reference to self here, because this key event could be the event of Q, for example, which will indicate that we need to quit, and therefore we need to set our exit boolean. And then, of course, we want to take in a key event here, which is a cross-term event key event. And as always, we'll return an IO result. In here, as I just said, we only want to check for one thing. We want to be able to close down our application. So if the event kind is equal to the key event kind press, and the key event code is equal to the key code character of a queue, then please exit by saying, okay, our exit variable is now true, and this will interrupt our main loop. So let's be brave for a second time and start our application. Now we have the process overview here again. The visuals haven't changed, but now I'm going to press the Q key and it closes down. Very nice. So at least now we have a way to shut down our application, which is always a good thing. Well, of course, we are still very, very far from the looks that we actually want to have. Especially one most important thing is still missing, which is the progress bar. So let's start working on that. For now, we'll need a second variable in here, because you saw that I have a kind of gimmicky feature. You can change the progress bar color. And to be honest, this is only a way to show you that in the end, the app will still be responsive while the background task is running. But of course, we need to implement this. So I'd say let's create a variable here, which is called progress bar color, and this is gonna be a Ratatui color. Now let's work on styling our application a bit. The first thing I'd like to change is I'd like to introduce a little vertical layout. This is because we'll have two sections to our application. One is the title section on top, and the other one is the section which will actually have the progress bar. So we'll take a layout, and it is a vertical layout. And now we have constraints, and we can input this in the sort of an array. The first constraint is going to be a percentage of 20%. This is the top vertical layout. And then we'll have a constraint of a percentage of course, 80%, which is the rest, which is going to be the bottom of our layout. And in order to use this layout, we will now have to get the areas from there, because in the end, when we want to render a widget, we always have to provide the area in which to render it. You can see that here, and not a layout. So we'll get the vertical layout dot areas. And the base area for this is going to be the whole area coming in here. And the return types are going to be, with the structuring here directly, the title area and the gauge area, which is going to be our progress bar. Of course, now we cannot, or we should not, render our title with process view directly in the parent area. Instead, we want to render this in our title area. Let us now create our long-awaited progress bar. So our progress bar is going to be a default gauge. This is a widget that is built into Ratatui, and it is one way it makes Ratatui very versatile and easy to use, because you don't have to care for creating this progress bar by yourself. It's just a built-in type, which is really nice. And then we can choose some style. For example, we'll use a default style, but then we'll use a foreground color for it. And of course, we're going to use our variable progress bar color for this. And we want to add a little label. Let's just have the process 1. And then we'll say, okay, this is at 50%. We don't really have a process yet. We'll just bake it. It's going to be 50%. And we'll set the ratio to 0.5, which will fill up our progress bar halfway. Now this would be kind of nice already, but as you saw in our final layout, I have a block around this. So let's create a block. A block is basically, I mean, you could say it's a frame. It's a frame around anything that can be drawn. So we'll use a block of the style bordered, and then we'll add a title to it, which is again going to be a line, and we'll call that background processes. And let's do a border set of border thick so that it's properly visible. And this allows us to set this block right here. And we're good already. So now the progress bar has some kind of block around it. And of course, we need the instructions that you already saw in the demo. So let's create those as well. The instructions are going to be just a line. And this time we're going to create that from a vector, because it's going to be multiple instructions. The first one is going to be for change color. And the into just converts this string literal into a span, which is the most elementary widget for text representation. To change color, we need to press the C key, and I want this to be in blue and bold. Then next to it, we have the option to quit, which is gonna be the Q key, and I also want this to be in blue and bold. So this seems to be quite fine. And then I want to have all of this centered so that the instructions are nicely in the middle. We'll now add those instructions as a bottom title for our block. And now we should already be set. We have a progress bar that has a block around it, and the block has the title background processes. And at the bottom, we have another title, which are our instructions. Let us now finally render this progress bar. So we'll call progress bar.render. And of course, we need an area and we need a buffer. Now I prefer to have this progress bar only be the height of one line, so I don't want to fill this whole lower area. So I'll create a new rectangle where our X starting point is gonna be the left side of the gauge area and the Y starting point is gonna be the top of the gauge area. Remember, for basically all graphical applications, the Y coordinate goes downward. So our 0, 0 is the top left. Then I want to have some width here, which is gonna be gauge area dot width. So I want to draw this by the full width. And the height is gonna be 3 lines, which will mean that the progress bar is 1 line of height, and in the end we'll have 1 line at the top and 1 line of the bottom taken up by the block. So this is gonna be very nice. Okay, we still need to import this rect from Ratatui, and the buffer can stay as is. Now we have an error still here because we need to initialize our progress bar color. And let's do this with, let's go with green. Why not green? Remove this unused import. And now let's give this one a shot and see how it looks, shall we? So let us fire up our terminal and run this. And we'll see this is exactly what we wanted. Our top 20% of the terminal, which is around this space, I guess that's correct, is taken up by the top of our vertical layout, and we have the title there. I mean, there's not much going on there, but it's a title. And the bottom 80% is our background processes. Of course, we've hard-coded to have just one process, but just let your imagination go wild. You could have 2 or maybe even 3 of them. And this one process takes up a total of 3 lines, the top and the bottom one taken by the block framing, and the internal one is just the progress gauge itself. Very nice. If we press change color, see, nothing happens, so we'll still have to implement that. But if we press Q to quit, we are quitting out. Very nice. So let's go ahead and quickly implement this color change. This should be quite trivial. So if our key event kind is still key event kind of press, and this time the key event code is equal to key code character, and it's a C this time around, then we'll just toggle between, let's say, green and yellow. So if the progress bar color is already green, then we'll say progress bar color is now color yellow, and otherwise we'll just set it to green. And this is still not quite right here. That seems more correct. So let's give this one a shot. We'll run it. And now if I press C, in fact, it changes between yellow and green. What a surprise! The visuals of our app are done now. They are not exactly a rendition of modern art, but enough to serve the purpose of displaying the progress of a task. If you would like to get deeper into the topic of Ratatui's widgets, you can find an excellent rundown on their website, ratatui.rs. What we are missing for our application now is the actual task we want to display the progress of. So in the second part of the tutorial, we need to implement a function that performs a computation. For simplicity, we'll simulate a computation using thread sleep. And while this works for demonstration purposes, it highlights a critical issue. If we run the computation task on the main thread, the TUI will block until the task finishes. For short tasks, this might seem harmless, but for longer-running tasks, it's a disaster. A frozen interface leads to a poor user experience, and as a rule of thumb, you should never perform heavy computations on the GUI or TUI thread. To solve this, we'll offload the computation to a separate thread. This thread will handle the task and communicate its progress back to the main application using a channel. While this approach decouples computation from the interface, we still haven't solved the following problem. As our code currently is, the TUI only re-renders when an input event is registered, meaning progress updates from the computation thread won't immediately trigger a re-render. This challenge brings us to the next critical step: designing a solution that ensures smooth and timely updates for our TUI. So the key challenge is handling input events and progress update events at the same time. Let's take a moment to explore two common solutions to this problem, each with its own strengths and trade-offs. Let's first look at a polling architecture. In this approach, we re-render the interface on a fixed schedule, for example every 20 milliseconds. Instead of using the blocking event read function, we replace it with the event poll. Advantages here are that the implementation is straightforward and easy to understand, and this would be ideal for simpler scenarios where responsiveness isn't really critical. Disadvantages, however, are that the TUI re-renders even when there are no updates, which does waste resources. In resource-constrained environments, this inefficiency might cause performance issues. And depending on the polling durations, inputs can have a short delay. Our second competitor would be the event-driven architecture. Here we handle input in a separate thread. This thread blocks on crossterm's event read method and creates a custom event whenever an input arrives. The computational thread also sends its progress updates as an enum variant of the custom event enum. Both threads communicate with the TUI thread using the same MPSC channel, allowing the run method of the TUI thread to block on the channel until an event is received. A quick note here, MPSC stands for Multiple Producers, Single Consumer, which is exactly the scenario we happen to have here. If you want a deeper understanding of channels, I can recommend watching my video on Rust channels. The advantages of an event-driven architecture would be that re-renders only occur when necessary, which conserves resources. And also we have better separation of concerns, making the code more modular and maintainable. However, disadvantages are that the implementation is probably a bit more complex, and we're requiring additional synchronization mechanisms. One additional thread is also required, which could be a consideration for highly constrained environments. So, summing up, each approach has its place and the right choice depends on your application's specific needs. For this tutorial, we'll focus on the event-driven architecture, as it provides better efficiency and modularity for a responsive TUI. Let's get our hands dirty with the implementation. In order to start with our event-driven architecture, it'd probably be a good idea to define our events first. I chose to make this an enum because enums are really powerful in Rust and it's basically exactly the right tool for this job. We have two event types. The one is an input event, and it carries data of a cross-term event key event. That's the only event we're interested for now. You could, of course, handle other events like this as well. And the other event that we are interested in is when a progress updates, and we'll have our progress defined as an F64 for now. Now let's create the functionality that our input handling thread will be doing. So for this I chose to just create a free function. So handle input events. And of course we will need some kind of transmitter to allow sending the events to the main thread. And this is gonna be an MPSC sender of type event. So we'll be sending events. In here we'll just infinitely loop, and we'll always block on matching this cross-term event read. And for now, let's just unwrap it. I mean, this is a tutorial, you know how error handling is done. For now, I'll just unwrap. That's okay, I guess. And let us implement some logic that is very similar to what we had in the main thread before. So we'll match on a cross-term key event, because that's the only thing we're interested in. And as soon as we'll get a key event, we'll send a new event. And notice this event is now a custom event. This was an event from the cross-term crate, so don't mix that up. And it's gonna be of kind input. Let's wrap the key event in there. And we'll unwrap the sending because, I mean, what could go wrong, right? It's basically nothing that can go wrong in here. And all the other events we'll just ignore for now. Of course, our second thread that we need to have is the background thread. And let's define in a free function as well what's going to be happening in there. So run background thread. Again, we'll need a tx, same as for the input thread. And well, what's going to be happening here? We'll start out with a variable progress, which is an f64, and it starts at 0, of course. And then let's just define an increment. So by how much will the progress rise for every tick, so to say, which is going to be 1%. And then we'll loop. Throughout this loop, as I said, we're going to just be using thread sleep to kind of mimic some whatever computation. So we're doing thread sleep for a duration. Yeah, let's get an update every like 100 milliseconds. I think that should be fine. So progress is going to be incremented by our increment. And let's just make sure that we're not surpassing 1 here. Otherwise, more than 100% progress seems a bit suspicious. And of course, after we've updated our progress, we're gonna send a progress event in which we'll wrap our progress. And we'll unwrap because what could go wrong? Now that we've implemented our background tasks, let's care about our app. In order to display the correct progress, we could have a member variable background progress, which is, of course, an f64, just as the progress we had in our run background thread. And the main thing we need to do here is change how our run function works. Before, we had matched on the blocking read, meaning that we always waited until we got a cross-term input event in order to re-render. And as I said, we should now be blocking on the receiving side of the channel. So of course, the first thing we need is a channel, which is gonna be an MPSC receiver side. And of course, we want to take in some events here. And now we'll match on rx.receive. And yeah, we could unwrap, we could bubble up here. It doesn't really matter for this tutorial. Of course, for production code, you should be doing a wise thing here, a more wise thing than unwrap. So we basically have two events that could end up here, which is an input and a progress event. In terms of an input event, we'll just do self handle key event of the key event, and we're good. And in case it's a progress update, we'll destructure it into a local variable progress, and we'll set our background progress to progress. Nice. And this already takes care of handling the main loop. You see, there's not much that changed. We're now matching on, or we're doing a blocking match on the receiving side of this channel, rather than doing a blocking match on the input, which allows us to have updates both when an input event comes in, as well as when a progress event comes in. Of course, what is left to do now is we have to put it all together in our main function. Let's quickly update the app here. We'll have a background progress of 0 initially. But now the main thing is, of course, let us create all of those channels and the threads and make them communicate. So let us create our main channel first. We have an event transmitter and an event receiver, which will come from an MPSC channel of kind event. So this is nice. As this is an MPSC, so multiple producer, single consumer, we can clone this transmitter side as much as we'd like, but the receiver side should not be cloned or cannot be cloned, because this one is going to be going to the app itself. So let's do this right away, and our app run function is already satisfied. So let's create one clone for our input events. We can clone this right away. And then we'll spawn a thread. And this thread always needs to move everything into the lambda that is required for the thread. And we'll handle input events here. And we need to provide our TX to the input events. And something is not adding up here. Yeah, one parenthesis too much. We'll do basically the same thing for our computational thread. So this is the TX to our background progress events. Again, we're gonna just clone this channel and we'll do a thread spawn, move, and this time we're gonna run our background thread with our TX to background progress events. And we forgot our curly braces here, and that should be all good. And if I'm not mistaken here, I guess this code should be all right. We create a channel, which the receiving side is wired to our app, and the transmitting side is cloned twice. We'll have one to handle the input events and one to handle the background thread events. And yes, we could have given the event TX here, right? Instead of cloning it. Well, that's not going to be such a big performance loss. So let's run this thing. Oh, cargo, run. Changing the color works. Progress is not updated though. Ah, yeah. That's probably because we still have hard-coded our progress down here. So we should be fixing this as soon as possible. So what we need is we want to have a 2-digit representation of our background progress here. So we'll have self.background progress times 100 to convert it to %. And of course the ratio should also be self.background process. So let's check again. Wonderful. As you can see, our progress bar is now filling by around 1% every 100 milliseconds. And while it fills, everything is still remaining responsive. So I can change this color. So we're handling input events just in time. I have no delay on there. And still the progress updates evenly. So we've managed to have a responsive process bar or progress bar, all while handling input events simultaneously and without any delay, which is exactly what we wanted. And that's a good basis for whatever apps you're going to be developing. And there you have it. We've successfully built a responsive TUI that handles inputs event and progress updates concurrently. Along the way, we explored how to offload computation to a separate thread, communicate via channels, and ensure smooth updates for the interface. This is just the beginning of what you can achieve with terminal user interfaces and Ratatui. From interactive dashboards to lightweight tools, the possibilities are basically endless. If you enjoyed this tutorial or learned something new, make sure to give this video a thumbs up and subscribe for more in-depth programming content. I'd also love to hear from you. what would you like to build with Ratatui? Let me know in the comments below. And as always, keep coding, keep learning, and I'll see you in the next video with Green Tea Coding.